Let's talk about arc length of parametric curves. So we've worked with arc length before, and we know that we can find a formula for the given length of a curve C, and if that curve is given by some function y is equal to, I change this to capital F because little f is the coordinate function for x of t. So we know how to find this arc length, right? So let's just quickly remind ourselves. We saw in the past that the arc length L is equal to the integral from a to b, and then we have the square root of 1 plus dy dx quantity squared dx, right? And if you'll allow me, we know that we can highlight this part right here. This part right here in red is really what we called ds before. All right, so let's calculate the parametric version of this arc length. And we need to do a little bit of work off to the side. So we need a parameterization of our curve. So we have our coordinate function x of t, and that will be equal to f of t. And our coordinate function y of t is going to be equal to g of t like this. And our values of t, let's say, range from alpha to beta. Okay. Now I can differentiate each of these coordinate functions. So my dx dt is equal to f prime of t. Dy dt is going to equal to g prime of t. Now, when we look at our integrand, we see we have a dy dx. So we've calculated what this was in the past. Our dy dx, that's going to be equal to dy dt divided by dx dt. Or you could write that as g prime of t divided by f prime of t. So let's work with this ds piece right here, and let's substitute in our dy dx and our dx. So we're going to have 1 plus, we're going to replace the dy dx with g prime of t divided by f prime of t. That whole thing is squared, so we're going to put quantity squared like this, and then that thing goes under a square root. So we'll put a square root there. As for our dx piece, we are going to obtain the dx piece by looking at our dx dt and multiplying both sides of this by dt to solve for dx. So when I do that, that means that I can replace the dx with f prime of t dt. And this lives outside of that square root. Okay. So what I want to do next is I actually want to move this f prime of t inside the square root. So what I'm going to do is I am going to have my square root of 1 plus g prime of t over f prime of t quantity squared. I'm going to have my f prime of t, I'm going to square that, and then I'm going to take the square root of that, and then my dt stays like this. So now that I have two square roots, I can move the f prime of t squared inside the square root there. So this is going to become the square root of 1 plus g prime of t over f prime of t quantity squared, and that whole thing is going to be multiplied by f prime of t squared. All right, dt. So I am now going to distribute this f prime of t squared across these square brackets over here. And when I do that, I am going to get the following. I am going to get the square root of f prime of t squared plus g prime of t squared dt. Now I can replace the ds in my original arc length formula with the square root of f prime of t squared plus g prime of t squared dt like this. I need to change my limits of integration. These guys were x values because it was a dx thing originally. Now they have to be t things. So here's where I use the fact that my initial parameter value is alpha. So my lower limit of integration should be alpha. And my upper limit of integration should be beta. All right. So this is all encapsulated in a theorem. If a curve is described by parametric equations x equal to f of t, y equal to g of t as t goes from alpha to beta, where f prime and g prime are continuous on this closed interval AB, or alpha beta, I should say, and c is traversed exactly once as t increases from alpha to beta, then the length of c is given by really this formula we wrote up above. So what I'm going to do is I'm going to highlight the formula that we wrote up above like this. This is using our functional notation f prime and g prime. And then I'm just going to really write the same formula, but I'll write it in Leibniz notation form. So this will be from alpha to beta. We're going to have df dt squared plus dg dt squared, all under 1 square root times dt. So let me highlight that. These are the same formula, just again, this one is in Leibniz notation. Okay. There is one takeaway that we need, and that is that we actually, through the course of this, found a nice formula for our arc length differential. And as we know, we need to use this arc length differential in order to do surface area. So let's write down our formula for ds. So ds is going to be equal to just that integrand part with the dt attached to it. So f df dt squared plus dg dt squared times, take the square root of that, dt. All right, so this is our formula for ds, which, in case you're wondering, is going to be important for us. All right, everyone, take care.